Bueno, chicas, dos chicas y chicos, bienvenidos otra vez al AstroTwin. Esta es la cuarta versión de este encuentro académico entre la Universidad de Leiden, el Observatorio de Leiden y la Universidad de Antioquia. Ahora va a pasar a inglés y bueno, espero que entendamos bien de qué se va a tratar todo el asunto. Okay, welcome to this fourth version of the AstroTwin meeting. In this occasion, we have the pleasure to have with us Carmen Toribio and Alan Hayes. They are teachers from the Leiden University, and I will ask you for your own presentation just in a few minutes, if you want, please. And remember, the courses is at the morning and afternoon every day. Check the web page for the test and the material of the courses. Every day we will have a quiz at 9 o'clock and afternoon at 1 o'clock. So, and of course, there will be the model web page of the course where you will did the proofs, the exams in the Moodle too. And remember that if you want a certificate, you can ask about after we finish. And if you want to take the course as a normal course in your matricula, how do you say matricula? I don't know. Remember that this is special topics in astrophysics, so only if you want. It's an elective course, so I will let you with Carmen. You will start, yeah? Ladies first. And this evening we will have Alan starting after lunch. So Carmen, welcome to Medellin, welcome to the University of Antioquia, and again, it's a pleasure for us to give you here with us. So, your students.
Okay, can you hear me well? Okay. Yeah, so I would like to thank you for this wonderful receiving here in Medellin. So we arrived on Friday night, and we are kind of, I think, adapted already to the schedule. It's a bit hard, but so I would like to give you a course on how to reduce ALMA data, and I hope at the end of these 2 weeks you will be able at least to understand how ALMA works and how to put your hands on ALMA data. Yeah, so I work in Leiden, and I work in the observatory, but in a small group which is devoted to do support to astronomers that want to observe with ALMA. So I work in a group which is called Allegro, and perhaps you don't know, but ALMA is a telescope. It's a partnership of many countries in the world, and in the case of European countries, every country that contributes to ALMA has a node, a group of people, experts, people that help astronomers to ask for time with ALMA, and also to reduce the data and get the most out of the data. So my work is basically help astronomers, other astronomers, to request time with ALMA, and also help them to reduce their data and to publish the results, basically. So I work for other astronomers, basically. So yeah, do you have a question?
I have a question. Do you? It's okay. Here. Is Colombia part of the ALMA?
No. No, I will show you later all the countries that participate. Thanks for your questions. Not yet. That doesn't mean that astronomers in Colombia cannot ask for time with ALMA. They can, of course. Everybody in the world can do it. But depending on the country of your institution, you will apply to different boards, let's say. So yeah, that's how it works. I will try to explain it to you later when I introduce ALMA. So they asked me to introduce myself a bit before, so you know me a bit. So when I was thinking on how can I explain them, who am I? So this is a Google Maps view of a part of Barcelona. I was born in Barcelona. I don't know if you have a pointer, perhaps? Or a stick or something. I can go there. It's okay. So, so this is a very easy to recognize. It's the football field of Barcelona football team, known as the best team of the world as well. So I was, actually I was born here. Ah yeah, excellent. Oh, I like it. So yeah. This is the Camp Nou.
Camp Nou?
Yes, and this is a maternity in Barcelona. So I was born there. Then I moved to live to my hometown, which is nearby Barcelona, with my parents for 18 years. And then I started university. And without thinking, I signed up for maths in the University Polytechnic of, in Barcelona, and which happens to be just here. So I came to study maths for 5 years here. And in my last year, I was thinking, oh, well, can I do the next? So I thought I would like to study astronomy. So I went to the physics faculty, which just happens to be here. And I asked them, oh, can I do a PhD? Yeah, of course, come in. So I did my PhD here. So I was 5 years here, another 5 years here. And yeah, I could, when I was doing finalizing my PhD, I could have very nice views because the Department of Astronomy is in the 11th floor. You can see the field, but you can also see a cemetery right here. So I thought, before ending up there, let's move a bit, right? So I asked for a postdoc abroad. And I went to, because I did my PhD in radio astronomy, I got a position in the Netherlands at Astron, which is here in the middle of the Netherlands. This is the Radio Astronomy Institute in the Netherlands, and they manage several radio telescopes. So I was working as a support scientist for LOFAR, which it is a radio interferometer which operates in very low frequency bands. And perhaps you have not seen this kind of antennas. You are used to the idea of a radio antenna with a parabolic receiver. Well, this is an antenna of LOFAR, and this is me. So you have the idea on the wavelength of the telescope. And so after 3 years there working for LOFAR, doing support for other astronomers how to use this telescope, I moved to Leiden here to work for ALMA, as I mentioned already, in the Allegro group, in the observatory, and we just happen to live in this building called the Oort building, which is a bit tilted. So yeah, this is where we work in Leiden. So more or less this is how, a bit of a brief story on where have I been living. And I will also explain you a bit what did I do during my PhD in case you had any questions. So one part of my PhD was to study the neutral hydrogen, the gas, in galaxies in the Virgo cluster. So this is the Virgo cluster, which is like thousands of galaxies all together, with a very bright intergalactic medium. So this is the core of the cluster with M87 in the center. And the galaxies that are falling into the cluster are suffering a lot of interactions among them and also with the intracluster medium, and they lose their gas. One of the most famous mechanisms is called ramp pressure stripping. So I investigated several galaxies here in the outskirts of Virgo that were supposed to be suffering strong interactions. And for that I used the VLA, which is an interferometer in New Mexico, with 27 antennas in a Y-shaped, and they change configuration depending on what you want to observe. So this, as an example, these are two of my galaxies. Now they are mine. So, and here in the background, perhaps you can see this is the optical image of the galaxy, and this is the H1 map. So here you have all the gas in the spiral that it's rotating, and well, the gas is the one that fuels the star formation, basically. So in radio is that what we observe in the 21 centimeter line. This is the kind of information that we retrieve from galaxies. So this was one part of my PhD. And next, also during my PhD, I was working with alfalfa. You know, perhaps you know the name because alfalfa is something that you grow. But Arecibo means, alfalfa means Arecibo Legacy Fast Alpha Survey. Alpha is the detector that they installed in Arecibo here in the feed. So this is the dish, which is in a valley in Puerto Rico. It's quite impressive. And then the detectors are up here. And alfalfa is basically a survey that tries to map all the sky in 21 centimeter. So they basically survey all the sky and get as much data that is coming from galaxies in this neutral gas. So this is a wedge diagram of all the galaxies that alfalfa has been detected. So as you can see here, there are around 11,000 galaxies. So that's impressive, that's a lot. We are used to this kind of numbers in optical surveys, but not in the radio because the techniques were not so evolved to have some larger statistics. So my work was to actually study the properties of all these galaxies and compare these properties in the radio with the properties in the optical. And next I moved to the Netherlands and I started working for LOFAR. And LOFAR is it's a different radio regime. It's much lower frequencies, so you detect other kind of processes in your objects. So here I show you the core of LOFAR. There are 6 stations here. This is in the middle of nowhere in the Netherlands. Well, nowhere. Okay, don't say that, but yes.
Something like an island?
Yeah, it's surrounded. So basically, the Netherlands, there is a lot of water in the Netherlands. So yes. they dump it out the water of this area here to make it as dry as possible, and the rest of the water is surrounding the core. Yeah, the super terp is called this. This is the LOFAR super terp. And basically, you have these 6 stations here, and then you have the rest of the stations are spread in a spiral way. So here is the Netherlands center, and then you have stations in UK, in France, in Sweden, in Germany, many of them. All this data is collected in these stations and is sent to a correlator in Groningen, where all the calculations are done. And then the data is sent to us, and then, well, to us, no, to Astron now. And then they process it, and then they deliver data to the astronomers. And for my science, actually, with LOFAR, I am working on M82, this nearby galaxy that suffers a lot of internal processes. And yeah, this is an image in the LOFAR band of the continuum of this target. You can see here there is a kind of a ring around the center. And what I'm working on now is to look for radio recombination lines coming from this target. So this is my own science, but of course this is not what I'm going to teach you. It's just so you know what is my background, and in case you have any questions regarding other type of observations, then you can ask me. So yeah, this is the goal of what I hope you can learn during these 2 weeks. It will be, I tell you, a challenge for me. I hope as well as for you, but it will be a challenge for me to try to explain you all this information. Because of course I have been helping people in parts here and there, but from the beginning to the end, like giving basics, it's quite a challenge. So yeah, I will first start doing some basic introduction to radio astronomy so you can understand what are we doing. I will explain you how ALMA works. We can put our hands on ALMA data, and we will try to learn how to reduce and analyze it. If we have time, I would also like to show you how we prepare proposals to be submitted to the committee to get time. And of course, we should also talk about the science that you can do with ALMA. So I will try to give you an overview of that as well. I submitted kind of a program. So I divided it in 9 lessons, more or less. Let's see if we can keep with that. So today I will give some basics of radio astronomy. If we have time, already starting a bit on how interferometry works. And for that, we need to know a bit of Fourier transform. Then we go to the labs, and we will use CASA, which is the main data reduction package that we use to reduce ALMA data, and of course other radio astronomy data it's also reduced with CASA. I will explain you the capabilities of ALMA and how all the processes, the workflow, how the data flows. I will like to explain you a bit how we calibrate data with ALMA, which of course the idea of ALMA is that the telescope already delivers images. So in principle, the astronomer should not worry on the whole process on how the data is calibrated and imaged. You should only be thinking in the science. But yeah, we are astronomers. We want to understand how things work. And it's important also to understand what are the implications for your data, to understand the calibration process. We will mainly be working on how to image the data, because in principle, the calibration should be done by a pipeline, which is clever enough, intelligent enough to do all this for you. You only have to do the calibration if there is problematic data, but that should not worry you too much. So we will be mainly working doing images to understand how imaging works in the radio regime, and then doing some analysis of the data, comparing what would go into a paper if you found something. And then finally how to prepare a proposal and give some hints on what is the kind of science that is being done with ALMA. Hopefully this is the program. But before we start, I would like to know some of your background as well, because I will need perhaps to adapt the way I explain things. If you already know everything, then we can just go to the lab and start working, right? So perhaps I would like to know how many of you are studying physics right now or have studied physics? You have studied physics? Very well. So no mathematicians here? Okay, you know more than me then. Chemistry, perhaps? No? Or engineering, or the full astronomy, because I understood that here it's physics and astronomy program. So who is studying astronomy?
Yeah, the rest is astronomy.
Okay.
Physics
Good.
and astronomy.
Good. Which year are you in? Like, are you in the last years of? No.
In fact, there are a few graduating astronomers right now.
Congratulations.
Morgan, Nicolas, and the other one are 6, 7, 8, 9.
9, yeah.
From the 5th.
Okay.
Semester, not year.
Semester, yeah.
So
I don't know. They look very young to me to have been here 10 years already.
10 years.
Well,
They study a lot.
it's a path that we realize you guys are 10 years older.
Yeah. Okay, so how many of you have done already some radio astronomy in your semesters? One only? So, okay. Good. How many of you are familiar with Fourier transform and waves and all these things?
Oh.
Easy. So, okay, I'm much more relaxed now. Yeah, how many of you have used Linux before in computing? Yeah, most of them. Good. And programming languages, I guess all of you have done and have usually used Python or all of them. Excellent. So I think we are good. We are good. All our fears are gone. So I will start here my course, but first perhaps it would be better if Alan gives his own introduction.
Do you want to introduce you right now, or maybe after lunch when you will start?
Shall I just start? Okay. Then, come in. Okay, so there is only one person, I think, that they did radio astronomy. I will provide you with this slide, so you don't need to write everything down. But I will give you here some links, because basically there is a lot of information out there already in radio astronomy, and it's very good. So they are like the first ones that started doing these, putting presentations online, were at NRAO in the US, the National Radio Astronomy Observatory. And they do a school every 2 years in one of the locations of the telescopes, or in the BLA or in Arecibo, depending. And they do this school every 2 years, where PhD students attend, and young postdocs, or even other researchers that just want to start working in radio. And yeah, they cover the basic topics, and they also do lab sessions. So yeah, all the information that is in their website is very useful in case you want to go deeper and understand, and yeah, perhaps do other tutorials on other data, because there is online data from the BLA, from many telescopes that you can just try and learn to reduce. So yeah, their website is very useful, and in the last years they have also been putting the videos, so then it's like being there almost. So I think it's very good. In Europe, they started the same initiative, so they have the European Radio Interferometry School, and it's also like every 2 years. The last one was last year, and yeah, they did it in Munich at ISO, and you have also all the lectures there and the tutorials. They do another one in Iran. Iran has the Plateau de Bure in France, in Grenoble. They also have very interesting material there. If you're a bit curious on how radio astronomy evolved, there is this book that they publish, and it's for free. It's online in the website. Serendipitous Discoveries in Radio Astronomy, and how was everything discovered during the 30s and after the Second World War. So it's quite interesting, but it's just kind of curiosities, and it's typewritten in Courier with a typewriter, classical typewriter, with curious pictures, and it's nice. I would recommend you this book, Tools of Radio Astronomy. I don't know if it's anywhere in the library or whatever.
I think we have a few.
It's a thick book. I have it there, so if you want to take a look, perhaps I have it with me. And something very useful is this book, Essential Radio Astronomy, which was officially published in Princeton University, blah, blah, whatever. But they have all the courses online available, and you can just navigate through it. It's in HTML, so it's very convenient and very useful. So to prepare this course, I have grabbed material from all these sources, and other, of course, but yeah, it's very interesting if you are willing to work with radio data. Okay, so this is the radio window, and yeah, so basically here you have the opacity of the atmosphere, and we will be working in this regime here. So all the data that it's in these wavelengths is defined as the radio wavelengths that we cannot see it. We use antennas to process the data. If you want to see a lot of all the telescopes that we have around the world in the radio regime, you could perhaps go to Wikipedia. It's incomplete, so you can, this is incomplete. You can go and fill it more, but there are more than 100 facilities around the world in the radio regime. And if you want to take a look to pretty pictures of telescopes, then there is this talk in one of the NRAO schools that collects a lot of pictures from different radio telescopes in different wave ranges. So it's very nice. So I will put you some examples so you can see a bit of a difference because it has implications in the technique. You work differently with the data if you use a single dish telescope like these ones. This is the Green Bank telescope, and this is fast. This is currently the new one in China, which is 500 meter dish. It's quite impressive. So yeah, the techniques work a bit different if you are using a single dish telescope or if you are using an interferometer. So here I show you the Westerbork radio synthesis radio telescope, which is quite linked to actually to Leiden, because it was built by the Dutch government thanks to the observatory in Leiden. At that time, it was Oort was the director of the observatory, and they pushed very strongly the Dutch government to build this facility, and that had very, lot of implications for radio astronomy to have this facility. It's located in Westerbork, here in the middle of, in the Netherlands. So you can see Leiden is here, and the telescope, is here, yeah. Here is Groningen, where I used to live. One extreme case of interferometer is the VLBI network. VLBI means very long baseline interferometry. And this technique is quite impressive because actually they combine radio telescopes that are spread all over the world. And so they point to a target, and as the Earth rotates, they combine the data of the telescopes that can see the source, and that actually allows radio astronomers to achieve the highest angular resolutions ever. Because radio interferometry in this VLBI technique, you can imagine it as if you had a telescope as big as the Earth. So it's very difficult to beat such a resolution, and these guys are the ones that have the highest resolution with the VLBI. And just to mention that actually in the next cycle, ALMA is also going to participate in this network. So ALMA will be also collecting data for VLBI, which is very, very important. Just for, to take it easy today, it's the first day, I will show you pretty pictures of ALMA. And so you understand how the telescope looks like, and where it's located, and why it has been done like this. You can see here the antennas of ALMA in the Chagnantor Plateau.
Carmen?
Tell me?
Sorry. How many antennas are working right now?
Yeah, you will see. No. I will show you. Yeah. So that's the final. The final array will be 66 telescopes. So it's located here in Atacama. I mentioned here the partnership. Sorry, these are the countries that participate, and depending on which institution, the country of your institution, you apply to certain time, because they divide the observing time depending on the partnerships. So Europeans apply to one of the boards, Americans to another one, East Asia to another one, and then Chile to another one, and the rest of countries to another one. And then this way they share the time. It's all about money in this world, so depending who puts more money, and then you have much more time or less. And if you, for instance, apply to Europe, it's very competitive because there are many people applying, but it depends. But it's important the country of your institution when you apply for time. But if you have good science and good proposals, then you should be able to get time anyway. So it's located at 5,000 meters, and this is because of the atmosphere at the wavelengths that we want to observe. The water vapor blocks the radiation that goes to Earth. So we want to be in a high place which is as dry as possible to put the interferometer. So it's not an easy task, and that's why it's only now that we have such facility and not 20 years ago, okay? And as you were asking, the final array will have 66 telescopes, but now, there are different kind of antennas. The main array is 50 per 12 meter antenna. Then there is the total power, which is 4 per 12. And then the Atacama compact array, 12 per 7. And I think at this moment, there are 40 of the 12 meter antennas. We can check later in the status, but not all of them have been integrated in the final array. So in the upcoming cycles, they will be adding more and more antennas. And it's good for the people that got time because they might have asked for a resolution and then they got much more because they add more antennas. So, yeah. Yeah, you can, in this location, in this website here, you can see Google Earth, the location of the interferometer and the observatory and everything, if you are curious. Yeah, so this is the frequency range that is covered by ALMA. At the moment we have from band 3 to band 10. Here I show you the transmission of the atmosphere depending on the millimeters of water vapor that we have on top of the array, right? Because even though we are in Atacama at 5,000 and it's super dry, you have some water vapor. So there are some clouds as well, so you have some water vapor. And depending on, for instance, if you have very dry conditions, you just have half a millimeter of water vapor, then you can observe in the highest subbands of ALMA. But if the weather conditions are not so good, are not so, they better choose to observe in the lowest bands, band 3, up to band 6, band 7. So every day at the telescope, they monitor constantly the time, and depending on the conditions of the atmosphere, they decide to observe in one band or another. Because at the moment, ALMA is, you cannot observe simultaneous bands at the same time. You have to choose.
Sorry, I don't understand why the level of, I think is water at the atmosphere is measured in millimeters.
Oh, well, because they use the water vapor radiometers at the antenna, at every antenna. Okay. Yeah, they use this to estimate. Basically, this is telling you, I will explain you later why do we measure in millimeters. Anyway, so this is just to tell you that even though the conditions up there are very good for this millimeter and 2 millimeter range, the weather also affects ALMA. And in this year, for instance, we had El Niño. You had it here as well, I guess. And that has prevented observing. Band 9 and 10 observations were very difficult to perform, so they almost did not perform because also ALMA was suffering from bad weather. Here in this link here, they have the atmosphere model, and you can put in, because perhaps you want to, when you want to apply for time, you would like to know how the results will be if I observe in band 7 or band 9, or depending on, so you can put some input there, and they will give you how ALMA would respond to your observations. We can try when we are in the lab. Yeah, so this is a view from the array. You can see all the antennas there. And this is the observatory site. The observatory site is at 3,000 meters. It's not at 5,000. So this is where the operations are done, and where the astronomers sleep, and the engineers as well. And during daytime, they drive up to the plateau if there is to do works there, and also if there is a problem, they have to go up. But in principle, everything is done from 3,000 meters there. Okay, so the important thing of ALMA, of interferometers basically that are mobile, right? So they move the antennas, and then you will understand why. So depending, there are different ways of moving antennas depending on the terrain. Here they had to build these tracks on purpose to move all these antennas. They are quite expensive, so you don't want to break them. And of course the terrain is a bit, difficult, so they are quite special tracks that they have had to build to move the antennas. Yeah, so you can see here how big they are. So the person goes here, so you have, there are people here. So you have an idea of the size of the antenna. So then, yeah, another pretty picture.
And
Yes, tell me.
after they put the antenna
Yeah, on the ground.
on the ground, they can move it?
No. That's what I'm going to explain. So they have made in all the desert several locations for the antennas. So they have made concrete surface where they bring the antennas and they settle them there. So the antennas are not randomly left wherever we want. They have several configurations and they are movable, but they go to a fixed concrete place
So they
in
need
the.
to make
Yeah, they need to put to build the concrete surface where they will put the antennas.
Okay.
Yeah. So
It's different because in ELA,
yeah, in the VLA they go in the rails.
roots.
Yes, and they can expand and contract the array along the rails. Westerbork is the same. You have several antennas that are fixed, but the last ones are on a rail, and then they also move it close and back and forth. But in this case, they move them with tracks, but they go to certain locations. Yeah. Yeah, so here you have what are those locations. So this is a cycle, last cycle of ALMA, last configurations that we have. So the most compact configuration is this one, in which the array has a size of about 2 kilometers. So sorry, this is 2 kilometers, this is the most compact, and then starts expanding until here. Now we move to, this is 12 kilometers, right? So they do this cycle from the most compact to the most extended to the most compact again. Yeah, so in the most extended configuration, the antennas are separated by around, I think the longest is 16 kilometers, which is quite big. And you have to think of this as a lens zoom. When you are with your camera and you are trying to take a picture of something that is close, nearby or far away, if you want to focus on something that is, you want to make it big, you extend your array, right? So the most extended configuration is used to pinpoint things that are small in the sky. And when we compress the array, we open the focus and we are able to see larger structures. So that's why they move the array, to change the resolution. Basically, the farthest away the antennas are, the smaller things we can see. And when we put them all together, then we open to the whole sky, ideally, right? So depending on the object that you want to observe with ALMA, you will have to apply to a certain resolution. And they will tell you, okay, if you want to observe a black hole, which is a super compact source, you will want to observe in the most extended configurations. But if you want to observe a big cloud in the galaxy, you may want to go to the most compact. So when you submit your proposal, you have to request for a certain resolution, and depending on your resolution, they will allocate your observations in one configuration or another, or in several if you want to combine different configurations, and you will learn why do we need such a combination later. Yeah, so this, sorry, yeah.
Why are the most extended configurations done in winter and the compact ones in summer?
Well, it depends on the year. This year they chose to do it this way.
Is there like a reason, or is it just because?
They try to actually, if in this cycle they did the compact in the summer, they will try to do in the next cycle the compact in the winter. So everybody has.
So they choose different configurations.
Yes.
In different.
Yeah, because if you want to observe in the highest bands of ALMA, for instance, you want very dry conditions, and
Summer or the winter, it's dry.
Yeah.
yeah.
And they don't want to move the antennas every day.
Yes. Yeah. So they try to cycle the configuration so everybody's happy and all the science goals are covered. If you want to observe in the higher bands with high resolution, you need extended configuration, but it's very difficult to calibrate. So, and then if you didn't get the good time this year, you can ask for time next year, and then perhaps the configuration will be in another time.
So the extended configurations look a bit random. Is that because of the shape of the Atacama means you have to have hills and...
You mean?
Because when you showed the pictures of that, they don't kind of spread around.
Yes, yeah, you have several hills in between. So yeah, they also need to take that into account. Because you need, ideally, you want your antennas all in the same plane as well. Because then otherwise you have to account for height effects that you don't want. It's a bit of a contradiction that astronomers are assuming a flat Earth, but that's the ideal case. And in the case of ALMA, for the farthest stations, the ones that are 16K, even though the elevation with respect to the main array is not very big, like 10 meters or even less, it still already has some effects. And also there are some different air currents because there are several hills that is changing a bit the atmosphere on top of those antennas. So it's very difficult to calibrate the antennas that are farther away. Yeah. And also this is not the final array, so there are still antennas missing. Once it's complete, it will not look as so random, I think. It will look much more spiral-like. Yeah. Yeah, this last configuration means, the 36 means 36 antenna. And in the next cycle will be 40 antennas and then go on. Yes, so apparently, I was not there when this happened, but apparently also the antennas are quite special. It's very difficult to observe in those frequencies. And in 1998, when they had the request of astronomers, hey, we want to observe this and that, they said, no, this is impossible, we cannot make it. But apparently that's what my boss told me, that finally they solved and they could manage to build. They are very,
Only 1 year.
Apparently they solved the problem in 1 year. Otherwise the project was totally impossible. So it's very...
They changed expert.
I don't know. But I think, it's very challenging, all the technology that goes into the antennas to be able to observe. So it's not only the altitude that you are going so high, the antennas and the receivers and everything that goes in there, it's very breaking technology. I'm not an expert on the engineering part, but I mean, it's quite interesting when you go there and you listen all the problems that they need to solve. It's quite difficult. So this is the page where the current status of ALMA is displayed. You have the weather conditions and also the status of the array. And the next cycle will start in October. And there it's listed the resolutions that the telescope will be able to achieve depending on the month. So you can see there the status. So it's dynamic. ALMA is very dynamic, and if you are wondering when are my observations going to happen, then you can go to this page and see when. Okay, so now you have seen what are we going to do, hopefully. But first we need to understand what are we observing. I hope everything is clear until now. Very easy, right? So what are we observing in radio? It's something that we cannot see. It's kind of strange, right? You are used to, you go at night, you look into the sky, you see the stars, but then in radio, what? Do we listen like in the movies, like Contact? Have you seen Contact?
Yes.
That she puts no? Jodie Foster in Contact goes to the telescopes and huh?
Amy Arrow. the right astronomer.
Ah, yeah. So she's from and she is sitting next to the BLA, listening to the waves. This is not what we do. No, we don't sit every day there listening to. There is a very nice experiment that they did. It's called Sounds of ALMA. So there is an astronomer there in Chile, Antonio Ales, and there is this electronic music festival, Sonar, which was in Barcelona and now is also in Santiago, and I don't know if they do it in other places as well. And they combined ALMA sounds, ALMA signals, they transform it into music, combined with electronic music, and apparently it's quite okay. So it's also a business, a way of, yeah. So yeah, Sounds of ALMA. You can look for it online, and you can, when you have a party, you can DJ with ALMA data. Okay, so we are not listening to the radio. If you want, you can do it. You just transform it to a right wavelength that you can hear, and that's it. But yeah, so we are collecting these signals with antennas, and then what, right? So what are we doing with that? So yeah, I would like to thank here to my boss, Remo Tilanos, because he helped me to prepare these presentations, giving me also some slides. So I'm not responsible for all the content, but I think it's quite good. So yeah, so usually in the other frequencies, we use the particle nature of light to get information, okay? Whereas in the radio, we use the wave nature. So the wave has amplitude, has a phase. So we basically, with the antennas, are measuring all the time, continuously, amplitudes and phases. And that's how it is, okay? Yeah, here is, I will show you, this is a plot of a picture of Jansky. Karl Jansky. You will be using this name all the time because we measure fluxes in the radio wavelengths. We measure fluxes in Janskys. It's a unit. It's named after this guy who first discovered cosmic radio wavelengths coming to the Earth. And I read it in these serendipitous detections of radio astronomy in the book, and also it's everywhere. He discovered these wavelengths by chance. He was working for Bell at that time. Bell, the phone company, wanted to transmit calls using certain ranges of radio, and there was a lot of interference. And they asked this guy who was a physicist working for Bell, to investigate the origin of all this interference, right? And then, yeah, he discovered this source of radiation coming from the sky, and then he published the results. So he was not a professional astronomer, but he was the first one to detect. And apparently he made this kind of construction using the engine of engine and wheels of a car, something like that.
For more.
Yeah.
Great.
Okay. So that's the question that we were trying to, because you need the intuition to understand then later what are we going to do when you analyze these images, right? So how we do transform all these radio wavelengths into images? What do these images mean? In this case, you have here, this is a group of M81 and M82, and this is the H1, the gas in these galaxies, and this is an interacting group of galaxies. So you have M81 here, M82, some satellites. And this is collected with a radio telescope. So how do we go from there, from something that we cannot see, to this, a map of neutral gas in these galaxies? Or this is this famous ALMA observations of HL Tau. We will work on this data, so get used to these beautiful images. And this is also a supernova detected by ALMA. Okay, so I hope at the end of today and tomorrow, you will have an idea on how do we make these beautiful images. So what are we measuring? We are measuring sky brightness, okay? So we are just measuring how bright is the sky in a certain direction. That's the only thing that we are doing. And if you, I already mentioned, it's very useful. If you want to go through this Essential Radio Astronomy book, you can go to the link, and then here you have the chapter, the introduction chapter on what are we measuring, sky brightness, blah, blah, blah. Okay, so I will just briefly go through some definitions on what do we mean by flux, this and that. So you are all physicists, you know better than me when you start doing all this. Let's assume this infinitesimal detector, right? Here. And we assume we have a source in the sky with a certain angle. So we are basically trying to measure the power that is coming from that source into our detector. So we define this brightness, which is the power that comes into our detector. And these are the units: watts per square meter per hertz per stereo radian. Sorry, my English is perhaps not very good. Are you getting everything? Okay. And then we have the brightness of the source, which brightness is independent of distance. That is something that you have to keep in your mind. And of course, we integrate that signal over the subtended angle over the source, right? And we have what we call the flux density. I think this is equivalent to in other wavelengths they also measure flux, right? So it's basically the integral subtended by the source of the intensity in the solid angle that you are observing. And this is the units again, watts per square meter hertz, once you integrate it. So this guy, Jansky, decided, hey, these units are not very useful because basically the sources in the sky are not very bright in these units. So you don't want to carry all along all these very low measures of flux. So it was introduced the unity Jansky, which is 10 to the minus 26 watts per square meter per hertz. And we will be basically working in Janskys all the time. Okay. And yeah, of course, if the source if the size of the source is very small, you can assume the cosinus is almost 1, and then you just have if it's the intensity, the brightness integrated over the subtended arc. And well, of course, you cannot do that, for instance, if you are talking about the Milky Way. The Milky Way is big enough, so you have to take that into account.
Why did he propose that number, like 10 to the minus 26?
Originally, I'm not sure why he chose that scale, but I think basically, depending on what he measured at the time, he chose the Jansky. I'm not quite sure on the origin of why minus 26. I just know that the number of sources that are higher than one Jansky in the sky are just not very much. So. Yeah, of course, you can integrate along the frequency axis, and then you get the total flux in the frequency range that you are observing. Oh, I thought somebody. What time is it, by the way?
The time is 9:40.
Oh, I'm going very fast. So perhaps, we can have a break after this. Oh, you are there. Yeah, that was a surprise. Yeah, I just wanted to put like a brief exercise for you guys to what a Jansky is, but then perhaps we can do it later, like writing down. I have another example there. Okay, that was just an exercise, so I think we can skip it. So this is the surprise slide for, for Alan. So we are measuring sky brightness and fluxes, but what all does this mean, like in terms of the physical processes that happen in the sources? For that you need an astronomer, like Alan, to come the idea, okay, how do we relate this sky brightness to something that happened in the source or in the way of these photons from the source to us, right? So I think Alan in his course will explain you, will give you some details on what are actually these measurements correspond to in the particles that are up there in the sky. Is that correct?
A little bit, yeah.
Okay. So if you have very difficult questions regarding what's happening up there in the source, in the chemistry of those particles, blah, blah, Alan is the right person. Yeah, so perhaps, yeah, I will explain you this example on this relation, right? So how do we relate what are we measuring with what's happening up there? So I assume you all have seen the equation of a black body radiation, yes? Okay. Okay, so yeah, we can basically figure out if we have a star up there, we can try to figure out what is the temperature profile of that black body. And we can just plot this diagram here. So you have the black body for different temperatures here, and this is the frequency. So you can see, like for 3000 K, you have this curve here, 1000, 300, and the coldest you go, the smallest you make this profile. But then you never reach those frequencies here, right? And that was one of the reasons, well, the main reason why professional astronomers didn't look much into the radio wavelengths, because they thought there was nothing happening there, right? If you think about a star that has like this kind of profile, you don't expect it to be bright in the nothing. Yeah.
Which range is radio?
Yeah, it starts here. Yeah. So you have the cosmic microwave background, 2.73 Ks, blah, blah, blah. Yeah, so it's microwave. Yeah, so the main reason why people were not looking into the radio is that they thought that stars were not emitting at those ranges. So that's why this guy, Jansky, found this. There was a first attempt of an astronomer to try to get radiation from the sun, but there was a lot of interference in his measurements, so he couldn't really get anything from the sun. But yeah, from the rest of the stars, the things that they were studying at that time, they didn't think there was going to be anything exciting at those ranges. Yeah, and you can, for instance, you can take a look to these lectures here where they explain this, a brief introduction on this. So yeah, what's happening there? So this is what we are going to look into in the upcoming days, and this is what Alan is also going to talk about, right? Yeah, I just wanted to finish this first part of the lectures with this picture of Jansky. And you can think about how we go from this to ALMA. So that was not too long ago, from 1932. So if you agree, we can take a short break now. Is that okay? What time is it? Okay. Sorry?